if we know that the zener is always going to drop its voltage, so the voltage across the zener and across the load is always going to be equal because those two are in parallel. So we always know that the zener is going to drop the voltage, RS is going to drop the remainder amount of voltage, right? And that's always, no matter if I have a load on here or not, that's always going to be the remainder amount of voltage of whatever the zener is in. So that's going to be our total current. So that never changes. That total current's never going to change. So I'm going to have all my, with the load in there, my current's going to come through and divide up. Some of it's going to go through the zener, some of it's going to go through the load. The two currents are going to combine and then go back through RS to get my total current. If I remove the load and my total current never changes, what's going to happen to my current going through the zener? It's going to increase. Okay? So that, remember, we have to calculate out that for the worst case, with or without the load. Remember, once we start increasing the load, start dropping the resistance down, all my current's going to start going through my load, and then I got to make sure I maintain enough current going through the zener to maintain regulation. That's my need current. All right. Any other questions on those eye clickers?
Yeah, you say number 9 was B, Kurt?
Number 9 was, does anyone know?
Yeah, it's B.
B.
But it could also be C, though.
Yeah, so I'm kind of curious about number 9.
I mean, the book mentions both.
Is that the one on the LED?
No.
In simplest sense, is interdiodes is really a reference.
Oh yeah, that one. Yeah, in the simplest sense, it can be used either for. It can be either used for a voltage regulator or a reference voltage, but in the simplest sense, it's really just a reference voltage. You know, so we're just giving on that other figure that we did, we're just kind of giving it a reference voltage. That's in the simplest sense. It's just a reference voltage. But yes, it can be used for either one. But yeah, that one I'll give you. You got either B or C. I'll give it to you. But in the simplest sense, it's just a reference voltage. All right. Any other questions on that? All right. Finally get to our transistors. Long and awaited.
Say what?
Finally there. So we're on page 781 now, our transistors. So now what we have is a transistor, or what we call them a BJT, or a bipolar junction transistor. So before, the diode was just had a PN junction. Now with our transistors, we're going to either have an NPN type junction or a PNP type junction. So depending on what we want for our current direction and our flow and what we want for our biasing voltage, we can either use either one, and they both function the same way. The one that we're going to look at is just, we're going to just look at it as, look at the NPN, but you analyze the PNP the same way, it's just that the voltages are flipped around. But you analyze them the same way. You just have to. So again, we just have that. We have the barrier potential between the two, and the one that we're really looking for is that we're going to have currents that are going to be going from our base to emitter and our collector to emitter. Those are our two basic currents that we're going to be looking at. So here's our two symbols that we're going to be seeing on our schematics. The NPN, and one way to remember that is that the arrow is pointing out. So if you just want to remember, if you're looking at the schematics and you're trying to figure out is that an NPN or a PNP transistor, what we use is just kind of a little abbreviation here. It says, we just say it's not pointing in. So if the arrow is pointing out, not pointing in, then that's our NPN. And in our PNP transistor, the symbol, the arrow is going to be pointing in, so we just call it pointing in. So those are our two types of symbols that we're going to be seeing on our schematics there. So when we're analyzing our transistors, here's our active component. So if we circle our active component right here, this is on the NPN. This is going to be our cathode side, and then on this side is going to be our anode side. So when we're first analyzing a transistor, we always have to make sure that we're looking at this, that our base to emitters forward biasing. So if we're looking at the transistor, which is a TO92 package, so if we have our transistor here, and we'll just say our transistor, the flat spot is facing us. It looks just like our 3-terminal regulator. But what we're going to have is that this is going to be our emitter, base, and our collector. That's what, and then on our schematic, it's going to be, here's our base, here's our collector, and then our emitter. Those are going to be our 3 legs that are going to be coming out of our transistor. The NPN, the one that we're going to be using is a 2N3904. That's our general transistor that we typically use, but there's a lot of different transistors out there. Some of them that have better frequency responses to frequency. But for general applications, the 2N3904 is the ones that we use. If we just want to turn on an LED, or if we just want to amplify a signal, then we use the 2N3904. If we're using something with high frequency or something like that, or need a certain amount of gain, we may go with a different type of a transistor. So we have our base emitter and our collector, and so what we have to do is that we have to make sure that we're forward biasing our base to emitter. So we know that this is, my base is going to be on the anode side of our active component there, and that's always going to have to be more positive than our cathode. And it's going to have to be more positive on our anode than our cathode by 0.7 volts, just like we do with a diode. We can just treat that base to emitter just like if it was like a diode. What's that? It is right there because it is a PN junction. Yes, exactly. So, because here's our collector is going to be our N junction, our emitter is going to be our N junction, and then our base is going to be our P junction. And so that is just going to be our PN junction, and we have to make sure that we're forward biasing it by 0.7 volts. Once we forward bias that junction, then what actually happens is that we start breaking down that barrier potential, and then the current starts to flow through our 2 N junctions, and then it starts to flow through our emitter to our collector. So the current's going through our base, and once we forward bias our base to emitter, that current is going to start to flow through our base from our emitter through our base resistor and then back into our source. Our base current is going to be very, very small. And that's kind of the whole idea. We want a very small amount of base current. We're going to turn on that transistor, and once we start forward biasing that transistor, then we get a large amount of current going from our emitter to the collector. So now so once you turn on that transistor, we get large amounts of current going through our emitter to our collector. And so just like any other solid state device, they're current-driven type of devices, so a small amount of current here produces a large amount of current from our emitter to a collector. So we have small amount of current from our base to emitter, and a large amount of current from our emitter to our collector. And it's, again, just like any other solid-state device, we have to have current-limiting resistors in there. So we're going to limit our current to whatever for our base, and then we're also going to have a resistor in our either on our collector or emitter to eliminate that current. So a small amount of current going through our base produces a large amount of current going through our collector to our emitter. So then the same thing with the PNP, it's the same thing. The only difference is that now our base, or our collector, we'll say our collector is going to be our P junction, our base is going to be our N junction, and our emitter is going to be our P junction. And on this one here then, because our arrow is pointing in, this is our cathode side, and our anode is on the emitter side, our BD forward biasing then has to be, our base has to be more negative than on our emitter. Okay? So the big thing is just remember, small amount of current on our base produces a large amount of current on our emitter to a collector. All right. So I'm gonna hand out so I printed out another sheet here that will kind of help us out figuring out all these currents in our gains and stuff like that. I was just going to go right to the collector to emitter amplifier, but I think that's all too much to take in at one time here. So yeah, so we can use our transistors for either turning on and off. We can use them as switches, or we can use them as amplifiers. We can either just turn on and off an LED, or we can use them for amplifying an AC signal. So we're going to start taking a look at them being as an amplifier. Yep. Okay, so what's this source? That one's 2 volts, and then this one was what? Yep. Yep. We'll take a look at that too. Yep. Because we got another curve tracer and stuff to hook up and stuff, but we'll take a look at that too. That's good, yeah. what the answers are. All right, so this is going to be one of our typical applications, and this is going to be the one that is also going to be kind of very similar to the configuration that's in Lab 33 for doing your what we call the characteristics curves. I just want to make sure you put your voltages on there. All right, so our VCC, we're talking about our VCC, that's going to be our voltage source for the collector. So actually this would be more VCC. And this one here is going to be our plus 15 volts. Our VBB is going to be our voltage source for our base. And we're going to have a plus 5 volts on that. Our base resistor is going to be at 470 kiloohms. And our collector resistor is going to be at 3.6. So just like any other solid-state device, what we need to do is we need to circle our active component, put in our polarities inside there, so we know which way to bias it. Then we bring over our soft voltages. So again, now we can just go ahead from our base to emitter. We can just treat that as an open. So if I treated that as an open, and I put my red lead on my base and put my black lead on my ground, what would I measure for voltage? My source voltage, and that would be what for source voltage then? My plus 5 volts. Now it's really critical that you make sure you use your red polarity, because if it was a negative 5 volts, we wouldn't be biasing that transistor. And then on my cathode side of my transistor or my emitter, what do I measure for voltage?
Plus or minus 0.
Plus or minus 0. So then we have to determine whether that base to emitter is going to be a go or a no-go. Is that going to be a go or a no-go? That's going to be a go. And if it's a go, it's just like any other solid-state device. It always takes its voltage first. And that voltage across the base to emitter is going to drop how much for voltage? 0.7 volts. So now once we determine that we did indeed forward bias our base to our emitter, then what we need to do is figure out what our voltage across RB is. Now remember that again, if I go from here to ground, I'm going to measure my 5 volts. And then as I add up my voltages, as I bring my red lead over to my ground, I should equal my 5 volts or my source. So what is that going to, what's RB going to drop for voltage then?
4.3.
4.3 volts. Now once you know two things, now we can determine our current. So what's my current going to be going through RB? Yeah, 9.149 microamps. So that's how much current we're going to have going through from our emitter to our base and going through RB. And also we should get our polarities in there. We know that this is going to be more negative, that's going to be more positive, so my current is going to come up from my emitter through my base, through RB, and then back into my source, and back to ground. Now, once we determine all our currents, all our voltages for our base, we can kind of just treat this as one separate circuit. Then we're going to treat this as another circuit. So now these are going to be, since these transistors are amplifiers, they're going to actually automatically have gain built into them. They're just going to automatically have a certain amount of gain. On a 2N3904, if we don't know what the gain of that transistor is, or what we call our beta, then what we use is just our beta is equal to 200. So if somebody doesn't give you what the beta is of that transistor, the internal gain of that transistor, then just use 200. And we're going to take a look at that. One thing about transistors is there's so much to know about them all at one time that it's hard to understand that. But we're going to come back and we're going to look at how to calculate out that beta. We're going to use what we call our curve tracer, just like we did with the diode, our 2-wire diode curve tracer. We're going to do the same thing with the transistor, and we'll actually be able to calculate out exactly what our beta is going to be for our 2N3904. But on the data sheet, it's going to be anywhere from 100 to 300 on the data sheet. When you're looking on the data sheet too, this beta, typically it's our beta DC. We also have a beta AC, which is very close to the same as beta DC. It's also called, if you're looking on the data sheet, it also can be called our HFE. That's our gain. So beta DC and HFE is going to be one of the same if you're looking at looking on the data sheets. Which one does? Oh, C, it does look like this. There you go. All right, so what we want to do then is what we need to do then is we're going to take for our approximations, then we're going to take our beta DC. And remember, these are current-driven devices. So what we do is that whatever our current is in our base, it's going to be multiplied by 200 times going from our emitter to collector. So to figure out what your collector current is, all we need to do is just take we're just going to figure out our collector current, IC, then it's going to be equal to ID times our beta DC. Okay, and that'll give us our current going through the collector. So what do I get for going to my collector? That's going to be determining what the current is going through RC.
1.829 or 1.8 or 1.83.
Yeah, I should get 1.83 milliamps. Okay, so there's our gain. So we only have a very small amount of current on our base, 9.149 microamps. Once we bias that transistor, what's going to happen then is we're going to produce a large amount of current on our collector. And in this case, since we're doing the approximations, it's going to be 200 times larger. Now once we determine our current for our collector and we know our resistance, then we can go ahead and calculate out our voltage across our RC. So what's my voltage across RC, or my collector resistor?
6.588 volts.
.588. So there's our voltage across our collector resistor. Now what we have is this junction here. This is our collector to emitter junction. Our voltage across our CE. Now as I start driving that harder, that resistance across this collector to emitter is going to vary. That resistance is automatically going to vary. What it's going to try doing is it's going to try maintaining, for approximations, it's going to be trying maintaining this beta DC of 200. That's the built-in gain of that transistor. So this transistor is automatically going to change in resistance to accommodate so that we get 200 more times current on our collector. So you can kind of treat it as, I'm going to erase this. So you can kind of treat it as this is going to be like a little variable resistor in there. And it's automatically going to adjust itself and change the resistance between our collector and emitter to maintain 200 more times more current on our collector than our base. And it's just going to vary that resistance in there. Well then, since we have this variable resistance in there, and we're just looking at our, so now we got our current, we got 1.83 milliamps of current going through there. We have this current going through our emitter, going through our collector to emitter, which is right here. Voltage of our collector to emitter. It's going to see that resistance. It's going to have a certain amount of voltage drop. Then it's going to go back, go across, go through our RC, and then back into my source. So the one in the red, that's our collector current. So since we don't have any other resistance other than this resistance of our voltage from our collector to emitter, then basically all it is then is we know that RC is going to drop 6.588 volts. We just have to take that number, take our 15 volts and subtract that 6.588 volts, and that's going to be our voltage of our collector to emitter. So what do I get for a voltage for my collector to emitter? And that is a test point, by the way, because we're going from test point C, which is our collector, to test point E, which is our emitter. So it actually does have polarities. So what do we get for our voltage then for
8.412.
Yeah, so and is it positive or negative? So we know my current is going, here's my polarity across my collector to the emitter, so is that going to be positive or negative? Positive. So my collector to the emitter voltage is going to be a positive. Wait, what did you say, 8 point what?
8.412.
412 volts. So that's going to be my voltage across my collector to emitter. If I put a voltmeter across there, that's the voltage I would need. So then if I were to measure my test points, assuming measuring my voltage source, I come around, bring my red lead around to my black lead, I should end up equaling my source voltage. So I'm going to have a plus 6.588 volts plus another positive 8.412 volts, and I get my total source voltage of 15 volts. Okay? So what's going to be my voltage from my collector then? So another test point. So here's my collector. Here's my red lead goes here. My black lead goes here. What's my voltage of my collector going to equal? Plus 8.412. Okay. And that can change depending on what we have for a configuration of our transistor. But in this case, it's the same as our voltage CD since our emitter is tied right to ground. So VC then is also going to be a positive 8.412 volts. All right, so now once you get into this, and then now the last question on there, it says, are we in cutoff or in saturation? Again, now this has to do with our diode characteristics curves. And what determines whether we're in cutoff or in saturation is that if we're in cutoff,
equals 0. IV will equal 0.
well, IV will have to equal 0 because we don't want to be forward biasing. So if we're in cutoff, when we're looking at cutoff, our voltage C to E is going to be equal to our source voltage. if I don't bias as base resistor, I can put my transistor into what we call a cutoff. What it's going to do is if I have zero current going into my base and I times it by 200, I'm going to get zero current going through my collector resistor or my collector current. So then that means that my voltage across CDE became open. Okay, just like a switch, it just turned it off. And what do I measure for voltage across an open? My source voltage. So if I'm in cutoff, meaning that transistor didn't get turned on, we're going to be measuring our voltage across our collector to emitter of our source voltage. Now saturation, our CDE, now for saturation, what's going to happen is that, now remember now RC is going to limit our amount of current that we can produce on our collector to emitter. This is going to be produce our current there. That's going to determine what our current is. Well, if I go into saturation and I take some number, let's say if this thing is in, like 3 milliamps or something, what's going to happen? I'm going to take my 3 milliamps, times it by 200, that's going to give me 600 milliamps. Well, it's impossible for me to get 600 milliamps with a 15 volt source and a 3.6 kilo ohm resistor. The numbers just won't work out. It'll go in what we call saturation. It's going to try getting a gain of 200, but it'll never get there. And this thing is going to try it's going to try getting rid of all of its resistance between our collector and emitter. That resistance between our collector and emitter is going to actually approximately go down to approximately 0 ohms. Now because of the PN junction and stuff like that, we actually can't ever get right down to 0 ohms going across our junction there. There's always some type of resistance. And so when we go into saturation, what we use for approximation is that we're going to end up going down to 0.2 volts. That's our number that we use. So if we go into saturation, then we just treat our collector to emitter dropping 0.2 volts. That's the smallest amount of voltage that our collector to emitter can ever drop. So when we're in cutoff, it's going to be our source voltage. When we're in saturation, that diode's going to, or that collector to emitter is going to go down to 0 ohms, drop approximately 0.2 volts. Going to be as much current as possible. So if this is just a short, then basically all we have is just this resistor and this source. And so whatever that maximum amount of current that can produce from that. Yep. And if we do end up exceeding that, then we're in what we call saturation. So now if we end up having a number, so our CDE here is positive 8.412 volts. So that means that we're somewhere in between here. We're not at our source voltage, and we're not at 0.2 volts. So that means that we're going to be in neither. We're going to be somewhere in between there. We're in neither. Yep, we're somewhere in between. So when we're treating it as an amplifier, that's where we want to be. We want to make sure that we're somewhere in between there, because we don't want to be cut off or in saturation if we're using it as an amplifier. If we're just using it as a switch, then we either want to be in cutoff or in saturation. We either want to fully turn on that transistor or fully turn it off. So if we're just turning on an LED, we want to go into saturation and turn on the LED. We want to shut that LED off, then we go into the cutoff situation. Okay? Any questions so far? All pretty straightforward so far? Sure. Or it should be. All right, so now we determined that we're in either state. We're not in cutoff or in saturation. We're somewhere in between there. And then our last thing is it's asking us for our emitter collector, or our current of our emitter. Well, we know that we got this current that's coming out of our base, going through our base to emitter. We got this current, and we have our collector current. Those two currents are going to combine right here, and then some of it's going to split up. Some of it's going to go back to the base of 9.149 microamps, and the remainder amount is going to go up through our collector at 1.830 milliamps. So our collector current, or our emitter current, then is equal to IB plus IC. That's how we determine what our collector of our emitter is. But typically, since we have such a small amount of current going through our base, for all practical applications, what we always just say is that IE is going to be equal to IC. So on your calculations or approximations, whatever you determine your current for your collector is, we're also going to determine that's the current going through the emitter. But in reality, it is that IE is equal to IB plus IC. But for approximations, we can just say IE is equal to IC. Alright? Now diodes look easy, don't they? Alright, any questions on this one before we try the second one?
Yeah.
Alright, let's take a look at the second one. So this is, now remember to kind of keep this in mind too, that we're going to kind of look at this same type of circuit, and we're going to be able to use that to determine our beta DC. This is kind of our same setup that we're going to be using. And after we're done with this one, then we'll go and look at our curve tracer. Alright, let's take a look at the second one here then. Alright, so we're going to have RB of 180 kilo ohms and RC of 18 kilo. Our voltage source for our collector is going to be a plus 15 volts again. And our VVV is going to be a plus 5 volts again. Alright, so what's my first step that I want to do? Yeah, circle the active component, and then inside your circle put your polarities of your active component, the negative, positive. Then what's my next step? Yeah, top voltages. So treat that base to emitter as if it was an open. And what would I measure for voltage at this point here? Plus 5 volts. And on my cathode side, yeah, plus or minus 0 volts. Okay? So my base emitter, is that going to be a go or no go? It'll be a go. And it's going to drop its voltage, and it's going to drop what for voltage? 0.7 volts. Okay, then once we determine that our base emitter is forward biasing, then we know that we're going to have polarities going across there. We know that my current is going to be going through that way. So I know that my current is going to be coming out of here, going up from my emitter to my base. That can be the source there. right, so once we got our current paths and polarities, we know that we're turning on our base emitter, then what's my next step going to be?
The RB.
Okay, so what do we need before we figure out the current dollar? Voltage. So what's my voltage across RB going to be? 4.3 volts. Okay? Now we can determine our current through our RB and what's that going to equal. What was it?
23.88
23.88 microamps. All right, good. Okay, so there's our current. Then what's our next step?
Figure out your beta.
Yeah, figure out our beta.
It's 200.
So it's 200. Okay, so we know that our beta DC is going to equal to 200. Then now what's my next step?
Figure out the IC.
IC, and how do I figure out my IC?
IB times 200.
Yeah, IB, so my IC is equal to IB times my beta DC. So I'm going to take my 23.88 microamps and then multiply it by 200. And what do I get for current of my collector there?
4.778 milliamps. 778.
Okay? Good. All right, then now what's my next step? Yeah, figure out the voltage across your RC.
17.20.
Try that again. 18.
Yeah.
So it should be 18 kilo ohms times 4.778.
Oh, see, I'm looking at the wrong thing.
Okay, so what did you get?
86.0.
86.0 volts. Is that possible? No, not possible. Because we only have a 15 volt source. We know that RC cannot drop 86 volts. We don't even have a source that's that big on our circuit. So what that's telling us, the minute we see that we get a large amount of voltage, we calculate a large amount of voltage across RC, we know that, am I going to be in cutoff or in saturation right now? I'm in saturation because RC is taking all the voltage. If I'm in saturation, I know that my voltage across CDE is only going to be 0.2 volts. It's like a switch. That thing is turned on so hard that it's like a closed switch. So it's just like measuring across the shore. So then we know that my voltage to CDE is going to equal what for voltage?
0.2.
0.2 volts for approximation. So if my CDE is going to take 0.2 volts, then what's my voltage? Now what's going to be my actual voltage going across RC then? Yeah, 14.8 volts. This is going to be actually going across my RC. So now we know that, so the things that we know for sure is that we're going to be at 14.8 volts across RC, and we know that it's an 18 kilo ohm resistor. So we know that that's not going to be right. So the two things that we do know for sure are these two right here, the 14.8 volts and the 18 kilo ohms. So now I can figure out what my actual current is going to be going through my transistor. What was it again? 822.2 microamps. Okay? So I'm going to have 822.2 microamps coming up through here, going up and through my emitter, across my emitter to my collector, across my RC, and then back into my source. So that's going to be my actual collector of my current. Now, since we know that we actually have a base current of 23.88 microamps and IC of 822 microamps, what we need to do is calculate out what our actual beta is going to be, what the actual gain of this circuit is going to be. So now our beta DC is just going to be, all we're going to just do is we're going to just take our IC and divide it by our IB. Since beta DC is the relationship between the base current and the collector current, and if we don't know the beta DC, then we can just go ahead and take the collector current and divide it by our base current, and it'll give us the actual gain of the circuit. So what's my actual gain going to equal then?
34.42.
34.42? Yeah. No units on it, just a number. That's going to be the actual gain of our circuit then. Not the 200, because we never could get that far. We are limited by our collector resistor. So our actual value of it is going to be 34.42 is our actual gain on that. So okay, so what's going to be my voltage of my, so we know my voltage of my collector to emitter is going to be a positive 0.2 volts. What's my voltage at my collector going to be? What's VC going to equal? So it's the test point, it's the voltage from my collector to ground. What's my, what would I measure for voltage? Yeah, positive 0.2 volts. That's the test point, so you have to make sure you get clarity in there. And then we already determined that we are in saturation. And once we're in saturation, then we have to recalculate it out with those values. Yep, two separate circuits. So this one always, this one's gonna, nothing has to be recalculated out in here because that's a whole separate circuit from here. Yep. The only thing that these two share is just that current of the emitter. Those two currents are going to combine right there, but 23.88 microamps is going to go off to the base, and the remainder is going to go back up through my collector. Yep, the two separate circuits, but you can see that we can get some gain. So this circuit would actually work like a switch. So I could go ahead and I could put an LED right here, and I could go ahead and put a current limiting resistor in there, put an LED in there, and my LED would light up with just a small amount of current. And we're going to take a look at transistors as switches later on after we get through all this. We've got some worksheets for transistors as switches and also as for LED drivers. All right. All right, any questions on that? Pretty straightforward. You anyone kind of start to understand? Want to see it again, or you want?
I got a question.
Good call.
It's because we are in saturation. Is that the reason why our data current is not going to be 200?
Why this current isn't going to be 200 times this?
Yeah, is that the reason why?
Because we're in saturation.
Okay.
Yep. We can only drive a certain amount, and it's based on RC. Yep. RC won't allow us to get more current than that. Yep. We're going to put that transistor, what we call, into saturation. It's only going to, because remember, what determines the current through the collector is this resistor right here. So if I lower this value of this resistor down, then my current would start to go up. as I lower the resistance of RC down, my current's going to start to go up, and so then with my beta DC, because since these are directly proportional, if I lower the resistance here, my current's going to go up. So if my current goes up, and IC and beta are directly proportional to each other, so if IC goes up, so does my beta. So if I get too much of a large resistor on RC, I'm going to run it into saturation. Alright. Any other questions? Or what else I can do too is I can also go ahead and I could increase. I could also increase RB. That would bring my current of my base down. If I bring my current of my base down, then as my current of my base goes down, my beta DC would go up, because those are inversely proportional. So you can play around with one or the other to accommodate for whatever you need. Yeah. So typically, a lot of times what we can do